the last part of thermodynamics. And so that means that Unit 4, we're kicking in on Monday. So Monday, Wednesday, Unit 4. But I like to tell people this is like a chemistry weekend because it's the weekend before your test. So I'd be working those problems at the end of this lecture, or is it the beginning? I think it's the end of the lecture notes. So I'd be working those. And if you have questions, you can always email me the questions or come by my office, you know, that sort of thing. If there were enough students, or if even one of y'all wanted to meet on a Tuesday, I can come up on a Tuesday too. Or we can do something with Zoom or something. Anyway, okay, what else do we need to know about thermodynamics? Well, we need to talk about phase changes, okay? So it takes energy to break bonds. That's usually pretty obvious. And by bonds, I mean intermolecular bonds and chemical bonds. And when bonds are formed, energy is released. And again, what sort of bonds? Those could be chemical bonds or intermolecular bonds. And just to kind of remind you what intermolecular bonds are, I think I talked about this before. Intermolecular bonds are the things that hold molecules together. Intermolecular, interionic. They are the things that keep, this animation won't work for me, but they are the things that, for instance, stick solid pieces together, whether each little ball is a water molecule. They are the things that, if we have less intermolecular bonds here as a liquid, and basically we have no intermolecular bonds here. Okay, so I don't know if that's ringing any bells. Lots of intermolecular bonds is solid. So that's what we're talking about, those things breaking. Okay, so when those things break, and you're going to see it kind of as you go from left to right, okay, solid, liquid, gas. See, energy, it takes energy. It takes E for energy. And then down here at the bottom, I'm going to say when they go from a gas to a liquid or a liquid to a solid, actually energy is released. So before we leave this slide, let's just kind of remember what we've been talking about. Does this make sense? Takes energy. Would that be endo or exothermic? Endo. It would be endo. So this is endo. And that means it's what? A positive Q or a positive delta H. And then down here at the bottom, okay, energy is released. Is that endo or exothermic? Exo. Yep, that would be exo. So that's exothermic. And that would be a negative Q and or negative delta H. Okay, we good with that? Those are phase changes, right? That's kind of what we're talking about here. So we're breaking bonds going from left to right. This blue up at the top, those are just the physical phases of matter, not including plasma because that just makes our life difficult. Solid, liquid, gas. We're breaking bonds as we go from left to right, and energy is required. Then as we go from right back to left again, from a gas to a liquid, or from a liquid to a solid, actually energy is going to be released. Those are exothermic. So we're going to dive into, how much energy does it take to melt something? You know, how much energy is formed when something actually, when a liquid freezes? How much energy is released? We're going to quantify those. You're like, do we have to? Yes, we do. So this is just kind of another kind of look at those three physical phases. From left to right, we have a solid, liquid, gas, and it kind of goes back to the kinetic molecular theory. Kinetic molecular theory, where all molecules, all atoms have a certain amount of kinetic energy. And actually it is associated with their thermal energy, and that's associated with their temperature. But solids have the least amount of motion and gases have the most amount of motion. And then we could go back the other way from a gas to a liquid, liquid to a solid, and we are decreasing our kinetic energy. Kinetic energy in motion. So then I couldn't remember, you got some boxes to fill in there. I think I just put the whole table up here. So fill away. Unless, is it on the next page? No?
Yep.
Yeah, there's a place to fill on anyway. I think we talked about this in Unit 1. We said, and however you want to kind of get it in your notes, now this time we have the physical phases going down. Solid, liquid, and gas. And the first thing that's talked about is size and shape. So I bet you guys would already tell me this. Solids have a definite size and a definite shape. Liquids have a definite size, but liquids take on the shape of their container. So liquids have an indefinite shape. And gases, oh my gosh, I love gases. Because gases take on the shape of their container and gases take on the volume of their container. So both their size and shape is indefinite. And then we go on to intermolecular bonding. That's the next column. So this is the IM bonding I was talking about before. Something that's a solid has a high degree of bonding. Jump straight down to a gas. Something that's a gas has no bonding. And a liquid is kind of in between. So it just kind of summarizes something that was said before. And then last but not least, we go on to, excuse me, a column for kinetic energy. And we said solids and kinetic energy, remember, is motion. The motion of those molecules or atoms. So in their solid state, solids have relatively low kinetic energy, gases have high kinetic energy, and liquids have something in between. So it just kind of summarizes the physical phases, kind of what they're doing, what they're all about. It was on that, yeah. Did you find it? So I'll go ahead and push this out there. Do you look at Twitter too? No? Okay, good. I'll put it on that Twitter. Okay, so these are some terms that you're already familiar with, okay? So when something goes from a solid to a liquid, we say it freezes, right? Okay. Oh, solid to a liquid. Oops, it melts. Shelby's looking like it freezes. Solid to a liquid, it melts. Okay. Okay, what about a liquid to a gas? Evaporates or vaporizes? Yeah, very good. Yes. And you can almost feel like if you want to melt something, you're going to heat it up. So you're going to add heat. So it's endothermic. Endothermic if you want to vaporize something to go from a liquid to a gas. Cool. Well, down here, what do we call it from a liquid going to a solid? Freezing. Yep. Very good. How about a gas going to a liquid? What do you call it when?
Compression.
It starts with C.
Condensation.
Yeah, condensation. Yep, condensing. You got it. Condensation. So for these ones down here, okay, bonds are being formed, and so actually energy is being released. So these are exothermic. Here in a minute, like I said, we're going to talk about the energy associated when matter changes phases. And these are going to be negative, the enthalpies. These are going to be negative, exothermic. And these are going to be positive, endothermic. Cool. All right. And that's just my slide doesn't work, that's okay. One other phase change actually is where it skips the liquid step. It skips the liquid. It goes straight from a solid to a gas. Let's see, so solid to a gas, that would be endothermic, seem right? Solid to a gas. And a gas to a solid, that would be exothermic. It gives off energy from a gas to a solid. The term we use for both of these can be sublimation, if something sublimes. I prefer to keep sublimation just for the solid going to a gas. The other day when I brought that dry ice, the solid CO2, okay, when it came up against temperatures of the room, then it sublimed. It went straight from being a solid to being a gas. I prefer sublimation for the first one, and then I prefer the term deposition actually for the last one. So deposition. Something goes from a gas to a solid. A good example of that is, did I mention this already, the whole frost thing? It's kind of like frost. So if you think about, we're bumping up against frost warnings, and let's just say it gets down to, I don't know, 25 or maybe 28 degrees Fahrenheit. And what's going to happen is basically that reaches the point where the air is saturated with regard to water vapor, but the temperature is such that it's not going to liquefy and form dew. It's going to actually go straight from being a vapor to being a solid. Okay, it's going to, we say, deposit and make frost. Another good example is if in your freezer, where basically you kind of had water vapor going around in your freezer a little bit to a certain extent, and if you ever have like frost burn stuff, yeah, that's actually deposition too. Okay, so I'll put both of these up here. We've been kind of talking how this works. Endothermic, exothermic. Endothermic, put energy in. What phase changes would those be? That would be the ones you think about heating to make it happen. So that would be melting and evaporation, or sublimation. Exothermic, again, to me, it's not as obvious because I don't think about drawing energy out of something to make it freeze, or drawing energy out of something for to have a gas to make it condense. Okay, but that's what's happening. Energy is released by those systems, by that matter, as they go through freezing or condensation, or I'm going to go ahead and change that sublimation to deposition.
Does it make sense to say, somebody tell me that it's, nothing can gain heat from the environment to produce, it's got to be something added to it. Everything loses heat. So if something, I guess I'm trying to.
I think you might be talking about the natural spontaneous things like the dispersion of heat, maybe.
Okay.
Because that's coming up in actually Chem 2. I'm going to kind of skip that for now.
Okay.
But I think. So I said we're going to quantify these things, and the way we quantify these things is with a quantity called latent heat. So there's a latent heat of evaporation, latent heat of melting, latent heat of condensation, latent heat of freezing, okay? There's a latent heat of sublimation, okay? There is. And our latent heats are going to take on the form of enthalpies. Enthalpies. So delta H, enthalpy change, VAP, means the heat or the latent heat of vaporization. Delta H VAP is latent heat of vaporization. What does it mean? It means how much energy, in this case, is required in order for a certain amount of stuff to vaporize. So it could be given in energy units per mole of material or energy units per gram of material. So So that was vaporization, this is condensation. What these both have in common, vaporization and condensation, is they're both dealing with the whole, the phases of liquid and gas. So one is liquid going to a gas, and this one is gas going to a liquid. Okay, heat of condensation. Energy per mole or energy per gram. Now this would be energy what? Released, right? So these should be negative. So if it's the same substance, okay, kind of going back and forth these last two slides, basically the energy required to vaporize is equal to the energy that would be given off as the stuff condenses, okay? But they will be opposite in sign. Well, so the amount given off is equal to the amount taken up. So we can say that the enthalpy of condensation is equal to negative enthalpy of vaporization for the same stuff. That makes sense? Now this really makes sense because you're like, dude, you wouldn't want to, because how do I say this? For all materials, they have their latent heats. Okay, that's the energy required per mole or energy required per gram. You look them up on the internet or look them up in a table. You would not want both of those values. That would just be silly. Okay, because we should be able to kind of make that leap. So in all of these cases with latent heats, the positive one is given. This just struck me today. Okay, so the positive one, the endothermic one is given. So in this case, you will find the heat of vaporization, not of condensation. Okay? So this one you find, delta H vap is there on the table, and delta H condensation is equal to negative delta H vap. Bottom line. Okay? We're going to see a similar thing with the other phase change, the whole solid and liquid. When I say there, to me, they're on table. How's that? Like there where? Okay. All right. Latent heats. So now we're going to look at the other pair. So the latent heat of fusion or heat of fusion is given as delta H sub fusion. Now, I guess I should say, if this is new to you, you're like, what in the heck is fusion? Fusion is melting. I don't know why. Fusion is equal to melting. Equals melting. I meant to look that up. I'm like, why did they go that route? I don't know. Okay, but it's basically the energy required to have something go from a solid to a liquid, and that's melting. Even though I didn't get right a little bit ago. Okay? So I don't know why we don't go with the enthalpy of melting or the heat of fusion of melting, but or heat of melting is melting. Okay. So without really showing you necessarily a slide for freezing, I bet you buy this, that the whole freezing and melting, or freezing and fusion, have the same amount associated with them, but they're opposite in sign. Okay, it's kind of like the evaporation and condensation. Okay, here we have freezing and fusion. And again, the endothermic one is there, so you'll see enthalpies of fusion. Remember, fusion and melting are the same thing. You'll see enthalpies of fusion, but you won't see enthalpies of freezing, latent heats of freezing. I think they just got cheap and they didn't want to mess around with the negative sign. So instead of having tables upon tables, I just have one table for you here. Okay, have some substances. So one of the things that bothers me, well, I'll tell you in a minute, but so we have some elements here. The temperature, and I'll try to explain why you need to know the temperature. But to work thermodynamic problems, you need to know that tipping point at which something, if it's warmer, it's going to be a liquid, okay, and if it's cooler, it's going to be a solid. And there it is. And then these are the heats of fusion, or enthalpies of fusion. If you want to put delta H sub fusion up there, you can. That's what they are. Okay. And then continuing on for the same substances, we have the boiling point temperatures. So this would be what? Going from a, excuse me, from a solid to a liquid. Okay, and these are going from a liquid to a gas. And these are delta H's of fusion. And these are delta H's of evaporation or vaporization. Delta H vap. Okay. Oh, what I started to tell you is this is just strange to me. Usually what I learned, melting points, it's like a small m, small p. When I learned boiling points, it's like a small b, small p. So anyway, there's our melting point temperatures and boiling point temperatures. And we're going to use those coming up. Okay, so down here we've got compounds with the same thing going on. I'm going to go ahead, if you want to draw a circle around it, you can. But let's see, we are actually going to be using benzene on the next slide. I inserted a problem. So these are what we're going to use for benzene. And if you're like me, sometimes I look at these tables and my eyes get crossed. And then to finish out this part, we're going to be focusing on water. So we're going to be using all of these values. One other thing, maybe just because, but do you see where actually just to kind of go back and forth between the energy per gram and energy per mole, all you need to know is the molar mass. You could do that. There's nothing special about these two columns that you couldn't manipulate around. Yeah.
So could you use kilojoules per gram?
Yep. Yeah. You could do kilojoules per gram. If I did kilojoules per gram, you'd probably just like take the first these numbers and factor in 1 kilojoule for 1,000 joules. Yep. Factor label though. So do you guys have this problem?
Extra, just
Okay. No. So somewhere in your notes, I added this problem a few years ago just because I think it's helpful to set up the last problem that we're going to do. So I told you we're going to pick on benzene. That's that C6H6. And I printed off this. This is actually just what you guys have. So this is how this works. And I brought my calculator because I don't have them worked in advance. So that's okay. Consider holding liquid benzene at the temperature of its boiling point. So that's if you look at, find benzene and find its boiling point temperature, and its boiling point temperature is 80.0. That's my point. Okay. It goes on to say we're going to hold it right. It's going to be in its liquid state. Okay. And we're going to, take it and we're going to change it, hold it 80 degrees Celsius, sorry, and we're going to vaporize it. So my choices here are 393, that would be joules per gram, or 30.7 joules per mole. But since that's in grams, I'm going to use the first one. So it's funny, I'm just going to say don't make this harder than it is. Basically, to work this, all we're going to do is take the mass, 54.3 grams, put it over 1, and I'm just going to use this energy per gram thing. So I'm going to go over here, and I'm going to see 393, and that's joules per gram for benzene. My grams cancel, I'm left with units of joules. That's it. That's the whole problem. Rounded to what? 3 significant figures. And I got wow, I got a big number. Oh, I want to do one other thing because we do this in the problems. It's kind of like one of the things that Shelby mentioned. I'm going to go ahead, and since this number is so big, I'm going to put it into kilojoules. So let's go ahead and introduce one more term. I got what? 1 kilojoule over 1,000 joules. That'll make it a little more reasonable. Okay. And 3 sig figs, I got 21.3. units are kilojoules, right? Any questions about that? Kind of a straightforward sort of deal. And then we're going to do kind of another straightforward sort of deal. It says what if instead of grams you knew it in moles, and you still want to know how much energy is released when you're going to vaporize 34.6 moles of liquid. How much energy is required? And that time I'm going to use the other one, which is the 30.7. So 30.7 joules of energy are required per mole. And let's go ahead and put it into kilojoules again. You're like, how do I know when to put it in kilojoules? Well, hopefully you'll just know. 1 kilojoule per 1,000 joules. And 3 sig figs again. I got 1.06 kilojoules are required. We good with that? Okay.
Would it have been okay if we just left it at joules?
Yeah. Yes, you could have left it at joules. Probably would have packed it up in scientific notation, but definitely. Either way, but the right sig figs. Okay, so let's do the last problem. So if you read it, you're like, it looks so short. How hard could it be? And it's really, really not that hard, but notice it says calculate the total energy needed, so it's going to be positive, right? And if you're drawing pictures, you're going to start basically with this chunk of ice, okay? And it's going to its mass is going to be 500 grams. But more importantly, its temperature is negative 50.0 degrees Celsius. Now, what happens if you add, well, I don't know if, I shouldn't ask this in the form of a question because I don't know if I was you how I would answer it. But we are going to assume it stays as a solid right up to its melting point temperature. So, I know you guys know what the melting point temperature of water is, but it's 0, right? 0 Celsius. So we're going to assume that it stays as a solid, okay, up to 0 degrees Celsius. Okay. Now, we need to know how much energy we're zapping it with in order to we're going to break it up into steps. We're taking it all the way, if you read the rest, and I'll go ahead and go right to the rest. The rest of the story is here. We're going to end up with steam. What phase is steam? Gas. We're going to end up with steam. It is hot in here, isn't it? Okay, we're going to have to do something about that. We're going to end up with steam. Here's my steam at a whopping temperature of 200 degrees Celsius. So we got two things going on here. We got the whole temperature change, and we got the whole phase change because, my goodness, it's going to have to go from solid to ultimately being a gas. So this actually is an application of Hess's law a little bit. Hess's law says that if you want to know something about an overall process going from negative 50 Celsius to 200 degrees Celsius in a phase change, if you want to know about an overall process, you can break it up into steps. It's Hess's law, just totally. So we're going to basically break it up into steps. This is going to be the first step. The next step is going to be to take the solid, and we're going to keep it at We're going to keep it at 0 degrees Celsius, and we are going to, here's my puddle, we are going to liquefy that thing. And again, I'll change my color to blue, and I'll say question mark E. How much energy does that take? But we're going to keep it at the same temperature. Then we're going to keep it as the same phase, and we're going to go from a liquid now. I'm going to keep it the same phase, sorry. Oh, go back. Now we're going to keep it the same phase, and we are going to go right up to the boiling point temperature, which you guys know what it is, but what is the boiling point temperature of water?
100 degrees Celsius.
100 degrees Celsius, yep. And again, question mark E. How much energy is required there? So I have 3 energies so far. It's like a little story. And then it's a liquid, and we aren't ready to go here yet, are we? We have to vaporize it. So we're going to take our liquid, and we are going to vaporize it. We're going to hold it at 100 degrees Celsius. Okay, we're going to vaporize it. And we're going to come up with an energy there. Whew. Okay, so now it's sitting at the boiling point temperature, 100 degrees Celsius. It is in a gaseous state. And now we just need to jack up the temperature of the gas. So now we're ready to go right for there. So question mark energy. All right, let's go back to this one. Let's go back to the ice cube. That is really cold, by the way. So I'm just going to tell you, and then you can mull it over, but to get to this energy, the change in thermal energy, we're going to use Q is equal to mc sub p delta T. It didn't change phases, it just changed temperatures. Then once we get it at the melting point temperature, for this phase change, that's what we learned today. That's where we're going to use the heat of, let's see, it'll be heat of melting, right? Heat of fusion. For that one, we're going to use our delta H of fusion. And the mass. I'll go ahead and put an M here. Mass times the heat of fusion. See how much energy it took to melt that thing. For the next one, when it's in its liquid state and we're just jacking up the temperature, we're going to go back to Q is equal to mc sub p delta T. See a pattern here? Okay. So once it's right at the boiling point temperature, then we're ready for our phase change again. So this guy right up here, that's actually now heat of vaporization. So I'm going to put M delta H vap here. And last but not least, if it's already a gas, it's going to stay a gas, but its temperature is going to be jacked up. We're going to use Q is equal to mc sub p delta T. I think I'll take a quick snapshot of this. I've never done this like this before in this class. So I'll push it out there on Twitter just for kicks. So let's execute the strategy. So these steps 1 through 5 actually correspond to my question mark E's 1 through 5 on the previous slide. First off, determine the energy needed to raise the temperature of the solid from its original temperature, negative 50, right up to its melting point temperature. Second, once it is at its melting point temperature, we're going to go ahead and melt the chunk. Okay, and we're going to use the heat of fusion. And then once it's melted, we're going to jack its liquid temperature up from right at the melting point temperature to the boiling point temperature. That's 4. And then it's right at the boiling point temperature and we're ready to go ahead and vaporize it. We're going to use heat of vaporization. And then last but not least, it's all in its gaseous state and now we just need to jack it up from 100 degrees Celsius to 200 degrees Celsius. That's it. So it's like 5 little energy problems. And if we add those 5 together, we end up with the overall total. All right? So here we go. So actually we'll need more than just this. This will help with the phase changes, but you also need the specific heat information. I've got it here, but that would be a different table, right? So this is an energy diagram. This actually, I kind of think of, this can be along the x-axis. You can think of it as time, or probably more appropriately, think of it as pumping energy in, okay? And for this anyway, along the y-axis is temperature. So we have that first one there, where we're going from, it's staying a solid, going from -50 to 0. And then we have a plateau there. Does that make sense? Because it's temperature staying constant, but we're pumping energy into it. It's temperature staying constant, but we're pumping energy into it. That would be our vaporization. Excuse me, you know what I mean, melting, sorry. That would be our melting. And then we have another section where we're going to go ahead and change the temperature of the liquid from its melting point temperature to its boiling point temperature. And then we hit another plateau where we're going to hold at the boiling point temperature, but we're going to vaporize the stuff. We're going to use our heater vaporization there. And then we have one more last stuff. It's gas, but we're going to heat it up from 100 degrees Celsius to 200 degrees Celsius. Okay, and we're going to use Q is equal to MC sub P delta T there. So I don't know if this will help, but like for the first one, I said we were going to use, that's where we're going to use Q is equal to MC sub P delta T. I'm going to go ahead and emphasize something down here. Does this make sense that it's a solid? We're going from, what, -50 to 0, but so we need to use the specific heat of the solid. The specific heat of water, you guys memorize, is 4.184 joules per gram degree Celsius. That's liquid water. Solid is different. So I'll put a little ice down there. And then the next one, the melting, that's where we're going to use Q is equal to the mass that we're melting, which is that 50 grams times delta H fusion. And this one right here, we go back to Q is equal to MC sub P delta T, and now the specific heat you're using is of liquid water. And then for vaporization, we got the Q is equal to the mass that you're vaporizing times the latent heat of vaporization, delta H vap. And then last but not least, up here for the last one, we're just basically going to jack up the temperature of the gas. So that's a Q is equal to MC sub P delta T. And now we have to use the specific heat of water vapor. I'll put gas H2O. So that's kind of what we got.
It looks like the biggest amount of energy is in the vaporization.
Yes.
And is
It's
that
drawn to scale.
typical?
Is that typical?
Of all materials? Or is that just for water itself?
I think it
Might be a
is.
little different?
I think it is. I'll have to think about that. That's a good point. She's saying that this amount of energy is significantly greater than any other energy, especially comparing to the melting. Don't know. Actually, I think it might have to do with water's hydrogen bonding. Yeah, so now we get to step through each of those, right? So the first one, we are simply taking the ice cube to the temperature of melting. So it looks like this. Do you guys have these already? Or you just have to do this part? Okay. Q1, the first Q is equal to the mass, which is, I said 50. It's 500 grams, or 3 sig figs, times, now this is where you'd have to look up the specific heat for ice. So you know it for liquid water, but for ice you would find it is 2.06, and that's joules per gram degree Celsius. And the change in temperature from that -50 to 0 is 50 degrees Celsius. And rounding to 3 significant figures, looks like for these, I'm tacking on a term to go ahead and convert it to kilojoules. 1 kilojoule over 1,000 joules. And now 3 significant figures, I get 51.5 kilojoules. And then on to Q2, which we shouldn't make it harder than it is. Q2 is simply melting the stuff. So you take the mass times the heat of fusion, just kind of like we did with the benzene. So it looks like this. The mass is 500 with a decimal 3 sig figs grams. The heat of fusion of water is that 333. Oh, I knew it. It says 338. See, I ran into that in my other class. Or anyway, this number doesn't exactly match with this number, but it should. That's the heat of fusion. Converted to kilojoules by 1 kilojoule over 1,000 joules. And 3 sig figs, I get 167 kilojoules. Now we are ready for Q3, which is to bump up the temperature of that liquid. Yeah, I hate that when my tables don't match my, I don't know. No, it's just the same one that's in your thing. Okay. So Q3 looks like this, where we're using Q is equal to MC sub P delta T. Again, this is the liquid. We're just basically going from the freezing point temperature to the boiling point temperature. So our delta T is 100, isn't it? So we take the mass, which is 500 grams, 3 sig figs, times the specific heat of liquid water, that 4.184 joules over gram degrees Celsius, times our delta T, which is 100, and I went ahead and gave it 4 sig figs, 100.0 degrees Celsius delta T, and then converted it to kilojoules with 1 kilojoule over 1,000 joules. And 3 sig figs looks like this, 209 kilojoules. So that's 3 of 5. So now, if we're telling a story, now it is a liquid right at the boiling point temperature, ready to vaporize it. So we come up with that heat with the mass times the heat of vaporization. And so the mass again is the 500 with 3 sig figs grams times the heat of vaporization, 2.26 times 10 to the third joules per gram. I'm going to see if this matches up. Yeah, that one matches up. And then convert it to kilojoules by putting 1 kilojoule over 1,000 joules. 3 sig figs, and I get 1.13 times 10 to the third kilojoules, otherwise known as what? 1,130 kilojoules. Phew. Then last but not least, now it's a vapor, and we're ready to jack the temperature up to that crazy temperature of 200 from 100. So we're going to use Q is equal to M C sub P delta T. So Q is equal to the mass, which is that 500 grams, 3 sig figs. The specific heat now of steam is 2.03 joules per gram degree Celsius. And the delta T from the 100 to 200, that's a 100-degree jump. And I went ahead and I think the 200 must have been given as to 200.0 degrees Celsius. So 4 sig figs there. Convert it to kilojoules, 1 kilojoule over 1,000 joules. Rounded to 3 significant figures. I get 102 kilojoules. Yay! Now we're ready to add those puppies up. Because they tell an overall story of taking negative 50 degree ice to 200 degrees Celsius. All right, So they all add up to, drum roll, we have to round to the nearest, looks like to the nearest, right here, tens places, because this guy right here. So that number is packed up in scientific notation, rounding to the nearest tens places. Because if you unpack this, you get 1660 kilojoules. That's it. Guess I should have. Any questions about that? I think this one, oops. I probably should have I should have said round to the nearest tens places, pointing to the 3 there. Okay, homework slide? Yep. Okay. Okay, so this is a summary of the story, and these are due on Marvelous Monday. Let's see if I've got them here. And I know some of you guys have to get out of Dodge, so. 7/29. I do. I'll just kind of show you the whole thing. So basically, these are my hints. And it's not entirely as complicated as what we did, but this one's very similar. And here's the next one. Oh, now I remember these. So this one, you have a phase change of gas, and it's cooling down to a particular temperature. So you have a term associated with the condensation, okay? And you also have a term associated with the cooling down of the condensate, okay? And you have a Q associated with the water heating up from the steam. So this is an example of within your system you have some kind of energy swaps. That's all the Q's are, energy swaps. They go like this. Within your system you have the steam condensing, you have the condensate cooling down, and you have the vat of water over here heating up. Okay? So I will tell you, it's like we ran into before, the final temperature of the cool down condensate will be equal to the final temperature of your vat of water heating up. They share the same final temperature. So, oops, sorry. The next one, see what your system looks like. You have a hot stainless steel ball, you're dropping it into water, the volume of the water is given, the specific heat of the stainless steel, the initial temperature of the stainless steel is given. And the thing is some excess energy vaporizes some water. Can't remember how this one goes. So you have an energy change of the ball, it's going to cool down. You have an energy change of the water, it's going to heat up. And some extra energy is actually going to vaporize a certain amount of water. How much water will that be that's vaporized? So within your system, here's your energy swaps. Your stainless steel ball losing energy, your water picking up energy, and some of that water picking up enough energy to be vaporized. Okay, so that's kind of how those go. One more? By the way, okay, you have everything except the mass of the water that vaporizes. Okay, ooh, There was one more? Come back here. 729. There we go. The last one looks like this. Oh, it's a classic. So you have a hot ball bearing, like stainless steel ball, mass is given, specific heat is given, the initial temperature, and you're going to rest it on a chunk of ice. Okay. Assume that the final temperature of the stainless steel ball will be the temperature of freezing point of water, which is 0. So your stainless steel ball is going to cool down to 0, and it's going to give off energy. That energy is going to be translated into melting a certain amount of solid. So your system really isn't that complicated. You have the stainless steel ball losing energy, okay? You have the ice picking it up and melting. Okay, all added together, they're equal to 0. Are they challenging? Yes. Can you do them? Yes. Will one of these be likely to be on the test? Yes. Okay. So honestly,